Well, thank you very much, Karen, Anna, Sibylla, and Hippolito for a really nice invitation to give a talk here. For those of you that have attended CAT's 21st, my series of talks will be very similar to the mini course I gave there. However, since I have been given a bit more time here, I will talk about some new results in the last lecture. So extriangulated categories were introduced in collaboration with Hiroyuki Nakaoka from Nagoya. I will start by motivating in the notion of an extriangulated category. So I will give three motivations. The first one is, well, it comes from an analogy with exact categories. So if A is an abelian category, then one can look at full subcategories E that are extension closed. So extension closed means that for every short exact sequence A, B, C, if A and C belong to E, then so does B. Okay. And such full extension closed subcategories of abelian categories have been axiomatized by Quillen under the name of exact categories. So the usual axiomatization that is used is closer to the one given by Keller. And for a nice introduction to the subject, there's a survey by Theo Bühler. Now in representation theory, a similar situation often arises from a triangulated category instead of an abelian category. So if C now is triangulated, then one can still talk about extension closed subcategories, meaning, well, the same meaning, but replacing short exact sequences by triangles. So if A, B, C, sigma A is a triangle in T with A and C in the extension closed subcategory, then B also belongs to C. Okay, we have seen examples of such extension closed subcategories in David's talk on stability conditions, and they appear in the choice of a slicing.
Yann?
Yes?
Can you use a different color than the gray?
Ah, okay, it's
Different.
okay, yes, it's hard to see. Yeah, okay. And so our first motivation here is to try and find an axiomatization for those extension closed subcategories of triangulated categories. Okay. Cool. And as more motivations, I will give two examples where this notion of extriangulated categories might not naturally arise. So the first example comes from the setting of an exact category. Let's see, be an exact category. And for those that do not know exact categories, you can start from an abelian category, and the situation is already interesting. And then fix some object P in E, which is both projective and injective. Then there's a quotient category, which is defined as having the same objects as E, but where morphisms are given by the quotients by the ideal of morphisms factoring through some power, additive power of P. So here, that means morphisms from X to Y that factors through some P to the N. Okay. Now, under some small restrictions, for instance, if E is small, one can define a group of extensions, which is going to be a bifunctor from E up times E, taking values into the category of abelian groups. And X1 will vanish in the first variable on the projectives and in the second variable on the injectives. So in both variables, it's going to vanish on P, which is both projective and injective, and hence it's going to vanish on this ideal. So it induces a bifunctor. Let's call it E on the quotient category C. So there is a sense about talking about extensions in these questions. And so the question is, can we talk about short exact sequences or conflations in C? So this is this question does not have a completely obvious answer. And to see this, we can look at a very well-known specific case. It's when E is a Frobenius exact category. So this means if E is Frobenius, means that every object admits a deflation from a projective object. So here P is projective, and an inflation to an injective object. And moreover, projective objects and injective objects coincide. So in that case, there's a very well-known result due to Happel that says that the quotient of E is the ideal of morphisms factoring through any projective injective objects is triangulated. It's canonically triangulated. So in that specific case, the images of conflations or short exact sequences have become triangles for a triangulated structure. So a second related example is an analogy between these results of Happel. So starting from a Frobenius exact category, and saying that the stable category is triangulated. And there's a related result due to Iyama Yoshino that's motivated by categorization of cluster algebras. And that's used to prove that there is a nice theory of mutation for cluster tilting objects, which considers triangulated categories T. And for simplicity, I'll assume here that it's 2 Calabi-Yau. So meaning that first it's home finite. So morphisms between two objects form a finite dimensional vector space. and that there's a duality. Let's say whom from x to the shift of y are naturally isomorphic to the dual, the k-vector space dual to morphisms from y to sigma x. And then one picks some object R in T, which is assumed to be rigid. So this means that it has no self-extensions, that is, no non-zero morphism from R to the shift of R. Now we consider a full extension closed subcategory of T defined as the X1 orthogonal to R. So that's a full subcategory on objects that satisfy R sigma X equals 0, or due to the two-Calabi property that X sigma R equals 0. And Iyama and Yoshino proved that then the quotient of C by the ideal of morphisms fracturing through some sum of copies of R is triangulated. So now to see that the analogy is more than just the conclusion is some category is triangulated, we can compare how shifts and triangles are defined. And in the Frobenius exact case, the shift is given by fixing for every object X a conflation or a short exact sequence X to some injective object IX, and then defining sigma X to be the co-kernel. This defines a functor on the stable category, and any different choice of short exact sequences would yield naturally isomorphic functors. Now on the triangulated side, instead of fixing an inflation to an injective, one fixes an approximation by some object in add R. This should be an add R approximation. So any morphism from X to R should factor through this approximation. And then one can complete this morphism to a triangle. And the cone on that morphism is going to define the shifts in the quotient category. So here's our shifts, and here's the shifts. Now to define triangles, there will be all diagrams isomorphic to diagrams coming from here conflations, X, Y, Z, where we look at this diagram here. And because IX is injective, there is an induced morphism from Y to IX that makes the left square commute. And thus it induces a morphism between the co-kernels. And that's how one gets triangles in the stable category. Now on the triangulated side, one starts from a triangle instead of a conflation, X, Y, Z, sigma X, where X, Y, and Z are in C, subcategory C. And we can mimic what happens on the left-hand side by looking at the triangle X to R, X to small sigma of X. And now we want to induce a morphism from Z to small sigma of X. And for this, we first rotate the triangle and look and the composition here, sigma minus 1z to x to Rx. And because z is in C, this morphism is the minus shift of a morphism from z to sigma r, so it has to be 0. By axioms of triangulated categories, it follows that there's an induced morphism of triangles. And one defines triangles in the quotients by taking all diagrams isomorphic to such a diagram here. Now the analogy also appears in the proofs. So the proofs are quite similar, but there are some differences, of course. First one has to replace conflations by triangles. Then the role played by the projective injective objects is, for Yamashita-Yoshino, played by this object R. So that was quite obvious from what I've explained so far. But another crucial point in the proof is that on exact categories, we often use pushouts or pullbacks, which do not exist in general in triangulated categories, but their role is replaced by the use of the octahedral axiom. Okay. So our aim, say today and tomorrow, will be, well, in 3 parts. First, we want to axiomatize, as I said, extension closed subcategories of triangulated categories. And we also want to describe or understand the structure inherited from an exact category to the quotients by some injective and projective objects. And last, we want to unify the theorems of Happel and Yamashita-Yoshino. So we would like a setting that contains those 2 results as special cases. So this. Okay. Yes, there was a question in the chat. So in that, the setting of a Yamashita-Yoshino, yes, projective injective objects are replaced by rigid objects. And yes, okay. And so the definition of a next triangulated category is a bit lengthy. But in short, it's the data of an additive category with an additive bifunctor E, which one should think of as some x1 bifunctor. And then we want this x1 bifunctor, so to have this notion of extensions, to be related to some sort of short exact sequences or of triangles. And there will be a realization that makes the link between extensions and such diagrams. So the realization S should send extensions, so say an element delta in EZX to diagrams of the form X, Y, Z, I, and P. Now, if you are in an exact category, an extension is not a short exact sequence, but rather an equivalence class of short exact sequences. So here we would like S to send delta to an equivalence class. Of such diagrams, where the equivalence relation is the usual one on short exact sequences. So IP is going to be equivalent to I prime P prime if there exists an isomorphism between Y and Y prime, making both triangles commute. Okay. And then we'll ask for some axioms. And all those axioms are going to be inspired from the case of triangulated categories, or more precisely, extension-closed subcategories of triangulated categories. Okay, so we have an additive category, a bifunctor that model extensions, and some realization that send extensions to, say, some sort of conflations. So now give more details. So let us fix the additive category C and the additive bifunctor E. And in order to define a realization, I will make use of some notations. So if delta is some extension and F a morphism from X to some X prime, then well, before giving the notation in full generality, I want to explain what happens in the exact case. So here, delta is represented by a short exact sequence or conflations, X, Y, Z, and F is a morphism from X to X prime. If we are in an exact category, then we can take push-outs along inflations. So there exists a push-out here, and this push-out gives a short exact sequence with a co-kernel Z, and that's usually denoted F lower star of delta, because the equivalence class of this lower short exact sequence is uniquely determined from the equivalence class of delta. Okay, so that gives F star a map, which is a morphism of abelian groups from X1 ZX to X1 ZX prime. Okay, and let's compare to the triangulated case. There, delta is a morphism from Z to sigma of X, the shift of X. And these morphisms can be completed to a triangle. Now F is a morphism from X to some X prime. And by composing here sigma minus 1 Z to X prime, we get a new morphism that we can complete a triangle. And because this square commutes, it induces a morphism of triangles. Anyways, the shift of F here. So we've got an induced extension epsilon that's obtained by a composition between sigma of F and delta. So here we've got composition with sigma of F induces the morphism from home Z sigma of X to home Z sigma X prime. Okay, so it turns out that starting from an additive bifunctor, we get such morphisms for free. So because E is a bifunctor, we do have a morphism of abelian groups, EZF from EZX to EZX prime. And by analogy with the case of exact categories, we're going to write that F lower star sigma, F lower star. And dually, E is contravariant in the first variable, so a morphism G from Z prime to Z will induce a new extension G upper star delta in E Z prime X. Okay, now we can define the notion of a morphism between two extensions. So a morphism of extensions from some delta in E ZX to delta prime in EZ prime X prime. So it's given by a pair of morphisms, U, W, where U goes from X to X prime, W from Z to Z prime, and such that, so they should satisfy some compatibility condition with respect to delta and delta prime. And we want that U lower star delta equals W upper star delta prime. So why should this make sense? Well, let's look at the corresponding equation for triangulated categories. So in that case, delta is a morphism from Z to the shift of X, while delta prime is a morphism from Z prime to the shift of X prime. And if we're given U and W, we obtain a morphism W here and a morphism sigma U there. And condition star says, well, U lower star delta is sigma of U composed with delta. We've already computed that above. And you can check that W lower upper star delta prime is delta prime composed with W. So what you get here is commutativity of the square, which is the condition required for U and W to induce a morphism of triangles. Now for exact categories, delta would be represented by a short exact sequence, X, Y, Z, delta prime by X prime, Y prime, Z prime. And we're given two morphisms, U, W. Now the condition U star delta equals W star delta prime precisely means here that there exists, so it's equivalent to saying that there exists some morphism of short exact sequences W, V, sorry. So a morphism V from Y to Y prime such that the diagram commutes. That can be checked as an exercise. So the notion of morphisms of extensions applied to triangulated or exact categories are the morphisms that do induce morphisms between triangles or conflations. Okay, so now a realization S. So as I said, it sends extensions to an equivalence class that I'll write with under brackets x, y, z. So that was for the usual relation on short exact sequences. And I will call an X triangle a diagram of the form X, Y, Z, IP, and delta, where, well, first delta is an extension in Ez of Zx, and the first part, the beginning of the diagram represents delta. So S of delta is the equivalence class of I and P. And yes, I will use the terminology introduced by Gabriel and popularized by Keller, by calling this an inflation, this a deflation, and both together called a conflation. So for exact categories, people tend to prefer the use of admissible inflations, admissible monomorphisms for inflations and admissible epimorphisms for deflations. But for general extriangulated categories, inflations are not monomorphisms and deflations are not epimorphisms. So I prefer that terminology here. Okay, now, so S as above is called an additive realization. If it satisfies 3 axioms. So the first one is that that morphisms of extensions should induce morphisms of X triangles. So for every diagram X, Y, Z, delta, and X prime, Y prime, Z prime, delta prime, and for any UW forming a morphism of extensions, so such that U lower star delta equals W upper star delta prime, there should exist a morphism V here, making the diagram commute. So here, UVW is called a morphism of X triangles. or a morphism of extensions, of conflations. Okay. Second condition is that there should be split extensions. So for every object x and z, there is an X triangle x goes to x plus z goes to z, which should realize the element 0 in the abelian group EZX. And finally, given two X triangles, X, Y, Z, delta, and the second one with the primes everywhere, then one obtains an X triangle by taking direct sums of those two. So there is an X triangle, x plus x prime, y plus y prime, z plus z prime, as you expect, where the corresponding extension is delta plus delta prime. So this should be an element in E z plus z prime x plus x prime. And to define it, we use additivity of the bifunctor E. So this is the same as EZX plus EZX prime plus EZ prime x plus EZ prime x prime. And the element delta plus delta prime corresponds to delta 0, 0, delta prime here. So a realization sends extensions to X triangles in such a way that morphisms of extensions induce morphisms of X triangles, and some natural additivity conditions are satisfied. So there are split extensions corresponding to the 0, split X triangles corresponding to the 0 extension, and direct sums of X triangles are X triangles. Okay, and that's almost it. So we can now give the definition of an extriangulated category finally. So that's the data of the datum of an additive category C, an additive bifunctor E taking values into abelian groups, an additive realization S, so that sends extensions to X triangles and satisfies the three conditions I've explained just before. And all these data should satisfy two more axioms. So, so the 83 says that, yes, so it's inspired from the case of triangulated categories, and it says that if you are given two X triangles, X, Y, Z, delta, X prime, Y prime, Z prime, delta prime, and a commutative square UV, then this can be completed to a morphism of X triangles. So there should exist some W making this square commute, and such that U lower star delta equals W upper star delta prime. So UVW is a morphism of X triangles. Now, because we want to axiomatize extension closed subcategories of triangulated categories, and those subcategories are in general not closed under shifts, we cannot shift X triangles. And so, unlike triangulated categories, where the opposite of the analog of ET3 follows from ET3, we have to assume it. So we want ET3 up, saying that starting from a commutative square VW here, there should exist some morphism U, completing it to a morphism of X triangles. And now the last axiom is the equivalent of the octahedral axiom for triangulated categories, or for exact category, the third Noether thirds isomorphism theorem. So it says that given an X triangle A, B, C prime, IP delta, and another X triangle starting at B, so B, C, A prime, delta prime, J, Q. So first one can look at the composition Ji, and the axiom says that this composition is again an inflation, and that the diagram can be completed to a diagram made of X triangles and morphisms of X triangles. So there exists a B prime here, and X triangles A prime here. Okay, where everything you can notice is a morphism of X triangles. So it says in particular that here, this extension is P lower star of delta prime, that delta is K upper star of epsilon, plus one last condition that you can see if you look at the middle cross. So this X triangle here and this one, you can see there's a morphism from A to B given by I, and a morphism from B prime to A prime given by R. And in the middle, you can put the identity from C to C. This should again be a morphism of X triangles. So such that also I lower star of epsilon equals R upper star of delta prime. So in the octahedral axiom for triangulated category, this last equation corresponds to some commutativity condition in the octahedron. Okay, so I will stop here for today, and tomorrow we'll see some consequences of the axioms and some more examples of extriangulated categories. Thank you.
Thank you very much for this very nice lecture. Are there any questions? You can put questions in the chat for Yann even later. And then we have a short break and have the last lecture by Lauren Williams at 5 past. Thanks again.
Thank you.